Module 8, Stoichiometry, Empirical and Molecular Formulas. In the previous section, we were able to figure out an unknown compound's chemical formula when we were given the product amounts of its decomposition. But there's a little more to consider here. We had to assume that the stoichiometric coefficient of this original reactant was 1, as you see here. But there are other ways to balance this reaction. What if we had 1/2 C2H8, or 1/3 C3H12, or 1/4 C4H16? Those equations are also balanced. We would just multiply both sides of the equations to get rid of the fractional coefficients, and any of these could be viable formulas. So really, the sample problem we went over in the previous section doesn't really tell us the exact chemical formula of the unknown compound. It lets us know the possible formula could be CH4, or C2H8, or C3H12, and so on. As long as the carbon and hydrogens are in that 1:4 ratio, there could be several accurate possibilities of the unknown substance, as long as it is a multiple of that 1 and 4. Yet, it is a very helpful process because we know our unknown cannot be many other possibilities. We therefore have a name for this type of molecule. To differentiate it from a molecule where we know exactly how many atoms of each type are in it, we have to learn some specific terms. A molecular formula is a chemical formula that provides the number of each type of atom in a molecule. An empirical formula is a chemical formula that provides a simple whole number ratio for the atoms in a molecule. So in our sample problem, the empirical formula we determined was CH4. But the molecular formula could be CH4, C2H8, C3H12, C4H16, or any other formula as long as there is one carbon for every 4 hydrogens. Well, with this information under your belt, let's look at some sample problems. The molecular formulas of 3 compounds are listed below. Determine the empirical formula for each compound: C4H12, Na2S2O8, and K2Cr2O7. Well, the definition of an empirical formula is the simplest whole number ratio for the atoms within a molecule. So we can look at the subscripts of all the atoms and see if they have a common factor with which we can divide them. Looking at C4H12, we know that 4 and 12 have a common factor of 4. So dividing both of these subscript numbers by 4, we get an empirical formula of CH3. That is the simplest whole number ratio of the C atoms and the H atoms. For Na2S2O8, we have 2, 2, and 8. They are all divisible by 2, so we divide them by 2 to get an empirical formula of NaSO4. For the last one, we have subscripts of 2, 2, and 7. There is no common factor for these numbers, so this formula is already an empirical formula. Though we don't know the exact formula of a compound when we only have its empirical formula, we do have a better idea of what it is made up of. And if we have the empirical formula for a compound and can find that molecule's mass, we can calculate the molecular formula. A compound's empirical formula is determined by experiment to be CH2O. In a separate experiment, the molecule's mass would determine to be 180.1 AMU. What is the compound's molecular formula? Well, in order to go from an empirical formula to a molecular formula, we have to multiply the subscripts by a common factor. To do this, we have to look at the mass of the empirical formula. It would be 1 times 12.0 AMU plus 2 times 1.01 AMU plus 1 times 16.0 AMU for a total of 30.0 AMU. Our given molecular mass is 180.1 AMU. We can find the molecular formula by asking ourselves how many masses of CH2Os are in our unknown molecule, or how many times does 30.0 divide into 180.1? We're basically looking for a common factor, so a common factor is equal to the mass of the molecule divided by the mass of the empirical formula, or how many CH2Os are in our unknown molecule. Dividing these numbers, we get 6.00. That means that if we multiply all the subscripts in our empirical formula by 6, we will find our molecular formula. We end up with C6H12O6 as our answer. We will go over another problem together, but first you need to learn another term. Molar mass is the mass of 1 mole of a given compound. So in our last problem, our molecule was C6H12O6. What is its mass? It has a mass of 180.1 atomic mass units. That means 1 mole of C6H12O6 equals 180.1 grams of C6H12O6. That is its molar mass, the mass of 1 mole of a compound. So if we know the molecular mass of a molecule, we then know its molar mass. If we calculate the molecular mass of CH4 to be 16.0 atomic mass units, then the molar mass, or the mass of 1 mole of CH4, is 16.0 grams. Conversely, if we're given the molar mass of a compound, we will know its molecular mass, or the mass of a single molecule of it. So if I tell you the molar mass of potassium chloride is 74.6 grams, then you will know that its molecular mass is 74.6 atomic mass units. Don't let this terminology confuse you. The terms are pretty straightforward. Molecular mass is the mass of a single molecule, so its units will be in atomic mass units. Molar mass is the mass of an entire mole of that molecule, so its units will be in grams. We need to use molar mass because it's a practical measurement. You can imagine that it's impossible to measure out a single molecule's mass, but it's much easier to measure out its molar mass, or a mole of that molecule, in grams. Let's try out this new information in a sample problem. A compound's empirical formula is PO3. If its molar mass is 158 grams, what is its molecular formula? Because we're given the molar mass of this molecule, we can figure out its molecular mass. It will be 158 atomic mass units. So we need to know what the molecular mass of the empirical formula is to see how many of those will divide evenly into the actual molecular mass we have. The mass of the empirical formula is 1 times 31.0 AMU plus 3 times 16.0 AMU, which equals 79.0 AMU. The common factor is the mass of the molecule divided by the mass of the empirical formula, which is 158 divided by 79, or 2.0. That means that to find the actual molecular formula, we have to multiply each subscript in the empirical formula by 2. And we get P2O6.